Welcome to our FAULHABER Drive Time. In this video, I want to show you how to operate such a third-party motor here. It's a slotted one, so different from what we usually use. And as this is a third-party motor, I obviously don't have such a flange adapter, so I will have to hold it in my hand. But that wouldn't be the big deal here. I'll add a disc here for us to see it moving. And of course, I have to connect it electrically, using adapters that I had to create here. One for the motor, Hall sensors, digital ones here, and the motor faces. And then the flat ribbon cable here of the encoder is using a different pinout than ours would be. So again, an adapter that I had to craft here. And let's connect this too. And then we are set and can start using the motor configuration window and the tuning window. And the main aspect here is I have to add this motor to the database of the Motion Manager. So let's take the PC and start working. So here I'm back with the complete setup. Now having the PC set up, I already connected to the motion controller, so you can see it's the MC5005. But first step would be to select a motor. And in that case, it's a brushless one, but obviously it's not part of our database. So what I have to do is create a new motor and enter a few identification parameters. Diameter is 40 millimeter, length is 56 millimeters. Shaft type is something more FAULHABER specific, so this would denote the type of standard flange that the motor does have. So that one is most likely wrong, but I don't care here. Nominal voltage is 36 volt and commutation type plus version. Again, FAULHABER nomenclature. I could add whatever letter I want, so use a B. And there is no special execution that I'm aware of. So, by the way, I could import such a motor data if I already added or created such a motor with another PC, and then I could exchange the data here. Next one is the real motor data, and therefore I have the data sheet of this motor in front of me, and the terminal resistance is 885 ohms, and then the friction. Yeah, friction is something that isn't included in data sheets, third-party data sheets. In that case, I used a FAULHABER motor of similar size and similar type, so a brushless one, because the friction is a parameter that we use for the calculation of the losses which are used for thermal protection. And then the torque constant of this motor is 75 millinewton meters per amp, and the inductance for the current loop would be 675 microhenries. And rotor inertia 44 grams centimeter square. Terminal resistance is included in this data sheet. If it isn't for your motor, try again with a motor of similar type and size out of our portfolio, and you should be set. And the time constants for the heat between the winding and the housing, it's 21 seconds, and then the one from the housing to the environment. An important one, number of pole pairs, it's a 7 here, and the rated current of this motor is, I think it's been 3 amps. Okay, I'll save that one, and then it's already selected, and then select the sensor systems that I'm having here. It's digital Hall sensors and an incremental encoder. That one is having 1024 lines per revolution, and I got a positive index here. And I'm going to use the digital Hall sensors for commutation, so that's block commutation or trapezoidal commutation, and the incremental encoder for speed control and position control. Once again, the check of the voltage and the preset of the overvoltage threshold here. I could change this later on. Transfer the configuration, and I'm finished here. I don't need to save it right now. And now the motor is indicated in the tree view, and next would be to actually identify the inertia of the disk here, and therefore I'm going to use the configure controller tool and try to identify the parameters automatically. I don't need to change the precision because I don't have any limits here, and but now I have to really hold this motor here when I start the identification, because a few steps are applied, and there is some force behind it, as you can see. Okay, inertia has been identified, and that's very similar to what the numbers here on my disk indicate. So it's a factor of roughly 20 between the inertia of the motor and the disk here. That's a high load. Summary of the parameters and transfer them to the motor controller, and we are finished here. Once again, I don't save them here. What I do now is use the controller tuning window, and as explained in the videos about the tuning in general, first start with a step for the speed control loop. Yeah, it's not too nice, but it will be as soon as we start position control. As mentioned in these cases, I usually would use the profile generator to activate the feed forwards, and to get some headroom for disturbance compensation, I usually reduce the profile parameters a little bit. I can increase the one for the deceleration here, because in my setup I'm having a braking chopper, which helps a lot in such a case. And then try to increase the gain of this loop here, and it feels stable. And now let me change to the position loop, and with a 1024 lines per revolution encoder, we got 4096 increment per revolution. And let's do one step here and check the behavior. Yeah, and what we see here, that's the speed here, the orange line, the dotted orange line here, and that's the triangular one, and the dotted blue line is the current, and it's up to roughly 1 time the nominal current of this motor here, so there would be some headroom for further acceleration. Otherwise, the following between the demand position in green and the actual position in red is pretty good. Can of course increase the gain of the loop a little bit, and try once again. Okay, so in general, following is good. I'm satisfied here. Of course, tuning can be for hours when you try to optimize, but we don't want to do this here. I can now save the parameters in the controller and close the window. And maybe one more aspect to be covered. Usually these brushless motors have different commutation sequences, and there is a setting within the special settings of the encoder using the drive functions window. And then in the encoder segment here, there are the advanced settings. And for digital Hall of non-FAULHABER motors, there are some options here. And in that case, the commutation sequence is Hall signals ABC of this motor. Ours would be ACB actually. In that case, it didn't matter because I used trapezoidal commutation. If I wanted to use field-oriented control and sinusoidal commutation, then I would have to check the box here before actually driving the motor. So for your information here. And I can apply this and send and finally save. And then we are done with this third-party motor. So far about how to operate such a third-party motor. Here a brushless one, a slotted design, so there is some cogging here. Wasn't the big challenge. I think the main influence here is we have to add the motor to the database of the Motion Manager, and then you can use it again and again. And of course, there might be the additional setting for the commutation sequence here. If you got any questions, especially to our motors, don't hesitate to ask our local sales team or contact our MC support team. And if you want to, please leave a comment below the video here. Otherwise, thanks for watching and check back with our channel, and bye.